Betelgeuse, the red supergiant star in Orion, has recently undergone an unusual phenomenon. Starting in December 2019, it unexpectedly dimmed, reaching a historic low in brightness by February 2020, termed the Great Dimming of Betelgeuse. This anomaly caught astronomers' attention, leading to intense scrutiny with powerful telescopes. They discovered that the star's surface is boiling, creating a fascinating cosmic illusion. Betelgeuse holds significance as one of the most captivating stars in the night sky. But what if Betelgeuse's timeline is completely off schedule? What specific factors triggered the unexpected dimming of Betelgeuse? And how does this relate to its stage in the stellar life cycle? Let's find out. Betelgeuse was born in a stellar nebula and spent 90% of its life in the main sequence phase, burning hydrogen into helium in its core. Due to its mass being about 15 times that of the Sun, Betelgeuse followed a different evolutionary path and evolved into a red supergiant instead of a red giant like typical Sun-like stars. Astronomers are particularly interested in Betelgeuse because it is rare to observe a star in its final stage of evolution with the naked eye, making it a valuable subject for studying the processes leading up to a supernova. The last significant supernova observed in the Milky Way was Kepler's supernova in 1604, and no other supernova has been observed in our galaxy within the naked eye limit since then. Therefore, any changes in Betelgeuse's behavior are significant. When Betelgeuse's brightness diminished, astronomers speculated that it might be a precursor to a supernova explosion. To investigate further, they used the Atacama Large Millimeter Submillimeter Array to closely monitor the supergiant. Observations from ALMA reveal that the dying star appears to be spinning rapidly, with speeds exceeding those predicted by current laws of physics. This was confusing. Why does Betelgeuse seem to be spinning faster than any other star of its age? Is this seemingly rapid rotation a sign of the impending supernova? The first indication that something unusual was happening with Betelgeuse came from the star surface radial velocity map provided by ALMA. This map visually shows the speed at which different parts of a star or planet move towards or away from an observer, using colors to indicate speed and direction. ALMA's observations reveal that one half of the star's visible hemisphere was blue shifted, meaning it was moving towards us, while the other half was red shifted, meaning it was moving away. These data were essential in measuring the star's rotational velocity. When these results were compared with Hubble Space Telescope observations, it was confirmed that Betelgeuse was rotating rapidly. One theory suggests this high rotation rate could be due to Betelgeuse having absorbed a lower mass companion star, a process known as celestial cannibalism. Although this is common among red supergiants, there's no conclusive evidence for this in Betelgeuse's case. If Betelgeuse evolved as a single star, its fast rotation is unexpectedly high. To understand why Betelgeuse's fast rotation is puzzling, we need to consider its size. Betelgeuse is 15 times more massive and about 1,000 times larger in diameter than our Sun. If it were in the Sun's place, it would engulf the Earth and extend to Jupiter's orbit. Betelgeuse is a red supergiant, no longer a main sequence star like the Sun. As these stars age and cool, they expand. According to the conservation of angular momentum, this expansion should slow their rotation. They also lose mass through stellar winds, further decreasing their rotational speed. Current theories suggest red giants should rotate at around 1 kilometer per second, and red supergiants like Betelgeuse even slower, typically less than 0.1 kilometer per second. However, Betelgeuse rotates at 5 kilometers per second, which is 50 times faster than expected for stars in its category. To solve the mystery of Betelgeuse's high rotation speed, astronomers had to confirm whether the observed rotation was accurate or a measurement error. They considered that other activities on the star's surface could be mistaken for rotational movement. To explore this, astronomers used the ALMA telescope, which has 66 antennas of different sizes and is one of the most advanced radio telescopes today. With ALMA's ability to observe sub-millimeter wavelengths of light, astronomers studied the hot gas in Betelgeuse's outer atmosphere. They wanted to determine if Betelgeuse's rapid rotation was actually a different surface activity. They suggested it might be convective flow, a process where stars like Betelgeuse move heat. In convection, hot material rises to the surface as it's lighter, while cooler, heavier material sinks, creating large swirling patterns called convective cells that look like giant boiling bubbles. These patterns can extend from the star's outer layer to its core. The team theorized that these boiling bubbles might create an illusion of rotation, with one group rising on one side and another sinking on the opposite side, making the star appear to spin by causing some parts to come towards us and others to move away. This movement could explain the blue shifted and red shifted regions seen in ALMA's maps. To test their idea, the researchers created a computer model of a non-spinning red supergiant star with a boiling surface similar to Betelgeuse. They compared the model's behavior with actual observations from the ALMA telescope. Surprisingly, the simulated star matched the real observations perfectly. This confirmed their theory that it's not fast spinning we see on Betelgeuse, but its surface bubbling like boiling water. This bubbling effect is so strong that even the most advanced telescope can't tell the difference between this and the star spinning. The study adds to the evidence of Betelgeuse's unpredictable behavior, which isn't new for astronomers. For example, the Great Dimming almost 4 years ago was explained by the star expelling a large amount of hot gas. As this gas cooled outside the star, it formed dust that temporarily blocked some of its light, making it appear dimmer from Earth. In 2023, Betelgeuse exhibited another strange behavior when its brightness increased by about 50%. Initially, astronomers thought this might signal a supernova explosion. However, further analysis showed it was actually a lingering effect of the 2020 Great Dimming. The massive release of dust and gas during that event disrupted Betelgeuse's usual cycles of brightness, which include periods lasting 400 days, 185 days, 230 days, and even up to 2100 days. The Great Dimming specifically altered the 400-day cycle, shortening it to 200 days and causing an unexpected increase in brightness. Predicting when Betelgeuse will go supernova is complex because it's hard to determine its exact stage in the stellar life cycle. Scientists need to know whether Betelgeuse is in the helium-burning phase or the carbon-burning phase. The timing of the supernova largely depends on this. At 550 light-years away, we have a prime view to witness this event. When a supernova does occur, the first clue would likely be a surge of neutrinos, tiny particles emitted in vast quantities during a supernova explosion. The supernova early warning system relies on neutrino detectors to detect early signs of supernovae. Following the neutrino burst, a supernova emits a vast amount of energy, becoming so bright that it can be visible during the day for 2 to 3 months before dimming. While a Betelgeuse supernova would be spectacular, it poses no danger from its distance. However, its absence would alter the appearance of Orion, as Betelgeuse is one of its shoulders. Despite its brightness, the James Webb Space Telescope isn't suitable for studying Betelgeuse accurately due to its sensitivity. JWST is designed for observing distant and faint celestial objects, making it unsuitable for predicting Betelgeuse's evolutionary age. If you found this information insightful, don't forget to like and subscribe to our channel.